So, hi everyone. In the morning's lecture, we just began with common emitter configuration. Okay, and we started with some very simple common emitter configuration, just a single transistor and a single resistor, and we showed you how to analyze a circuit like that. And I took an example of your tutorial example. So I'll solve the numerical now. And in the morning, I just told you how to solve it and left it. So in the example given in your tutorial, the question goes like this. You are supposed to find the voltage gain V naught by Vi in the first case and the second case. The first case is when your beta is infinity and the early voltage both are infinity. If your beta is infinity, automatically you should see that your R pi is infinity. If VA early voltage is infinity, then R naught is infinity. So your small signal just reduces to something like this. This is your small signal of your BJT, so GM V pi, and there is an RL, there is no R naught because R naught is infinity. The voltage across this is V naught. This is V pi, and this is RS, this is VA. So now if you look at this, no matter what the value of RS is, what will be the value of V pi in terms of VI? VI itself, right? Because there is no current flowing through this. So V pi will be equal to VI itself. So that's an interesting result because it tells you that your voltage that is being fed to the common emitter stage, the voltage that is fed to this amplifier is independent of RS, provided you satisfy this condition, which is Rn is infinity. If your Rn is infinity, then the voltage gain will have no dependence on Rs. Okay, it will have no dependence on Rs. So that is one advantage. So whenever you are designing a voltage amplifier which has to take voltage as an input, you will usually try to achieve as high an input resistance as possible. Okay, if you have seen in the previous lecture also I discussed, for ideal voltage amplifier input resistance should be infinity. So that's what happens here. So if Vin equals V pi, then you can directly write the value of V naught. I told you guys, just of course you can use KCL at this node, Kirchhoff's current law at this node, and write it this way: GM V pi plus V naught by RL equals 0. So V naught is this voltage equals 0. So your V naught will be equal to minus of GM RL into V pi. Okay, but I said that it will be easier if you can visualize it as a current flowing. You can visualize this as a current of value minus GM V pi flowing in this direction. Then this current is going to flow into the resistor and create a voltage drop which is equal to this minus GM RL into V pi. So the voltage gain in the first case is minus of GM into RL. So the question is given IC is 1 milliampere. So your GM is ICQ upon VT, the thermal voltage. So that is 1 milliampere upon 25.9 millivolt. Okay, yeah, so millivolt at 300 Kelvin. So this value comes to around, I think, 26.7 milliampere per volt. So is that the value for, you get around 26.7, 1 by GM, VT by IC is 1 by GM comes at around okay, so that's okay. So you can calculate the value. Does anyone have a calculator? I mean, you can just quickly try it anywhere. So you can just report the value. How much do you get? AV is minus 10. Maybe I don't know the value. I'll check it. So then, oh, okay. This is actually, it's 10. Minus 10 is the gain. Yeah, I'm sorry. I think I've chosen the values in such a way I forgot now. See, I've given RL as 260 ohms. So the question was framed in such a way that 1 milliampere per, I think 10, 38.5 milliampere per volt, you're right. GM is for a milliampere, it is 38.5 milliampere per volt. Yeah, so I'll take 26 millivolts. VT has 26 millivolts. So 26 millivolts into 260. So this comes to around 10, I think, right? So million, yeah, you get it around 10. Minus 10 is the gain, volt per volt. So if we ask you to express this gain in decibels, what will be the value of the gain? In decibels. So whenever you are expressing gain in decibels, No, it should be plus 20. So the gain will be, so always express your gain like this, 20 log of mod of AV. You should express your gains in terms of decibels. So 20 log of, take magnitude and then express it. So that will be 20 log of mod of minus 10 is 10 to the base 10. So you will get 20 decibels. Okay. So logarithm itself cannot be negative. So some of you written minus 20. Minus 20 will happen if the gain is 0.1. If the gain is 0.1, then you will get minus 20. Okay. So if the gain is 1, if the gain is 1 plus or minus 1, you don't care about the sign. If the gain is plus or minus 1, then you will get 0 dB. Is that okay? So 0 dB is the gain. So we'll later talk about how to express gains in logarithms and all that. We'll come to that a little later. But right now, you should be able to express gain in terms of decibels as well. So generally, decibel will be a ratio quantity. You express it ratio of two quantities. Okay, that's the way you express it in gain. We'll solve the second problem. In the second problem, it's given that so Gm into RL, the factor Gm into RL is 10. So keep that in mind. In the second case, it's given that Va is infinity. So that's fine. R0 is still infinity. But beta is 100. So beta is 100, then R pi becomes finite. R pi is how much? Beta into Vt upon ICQ. Okay. And that turns out to be beta into Vc upon ICQ. So that is around, I'll take Vt as 26 millivolts, 2.6 kilo ohms. Okay. So it is 2.6 kilo ohms. 2600 or 2.6. If you assume Vt as 26 millivolts, yeah, that's okay. Vt, take it as 26 millivolts. 26, 25.9 or 26. So this is your R pi. Now Rs is given to be, so now instead of open circuit, you are going to have an R pi here. There is going to be an R pi here. So what will be the voltage V pi in terms of Vi? Is that okay? Because it's 2.6 ohms. 2.6 kilo ohms. Rs is also given as 2.6 kilo ohms. So you have two equal resistors. So whenever you have two equal resistors, voltage division will be half. So V pi will be Vi by 2. Okay. So now what will be the voltage gain? Your voltage gain is minus of GMRL into V pi, which is nothing but minus of GMRL by 2 into Vi. So GMRL is 10, 10 by 2 is 5. So the voltage gain is minus 5. Okay. So can you express it in decibels? How much will it be? 20 log of 5 will be 4 decibels. Is that okay with you? I'm sorry. 20 log of 5 will be 14 decibels. Okay. So there is a general rule of thumb. So I'll teach about logarithms once we go to frequency response in greater depth. But right now, you can just take it this way. So whenever you have a quantity, let's say you have 20 log of x by 2. You are dividing it by half. Then we do something like this. 20 log of x minus 20 log 2. This is just a logarithm operation. The value of 20 log 2 is minus 6 dB. 6 dB. Always remember this. 20 log 2 is 6 dB. Okay. So we normally say if the gain has become half, in decibels it will reduce by 6 decibels. So that's a rule of thumb. They will teach you in greater depth in control systems. Everywhere you will encounter the 6 dB word. I'm just telling you now. So your gain will reduce by 6 decibels. That's one rule of thumb that you can remember. Okay. So that's it. I've solved this second question as well. The gain will become 5. So that's what I think. So 10 is in the first case. Second case it will be minus 5. Okay. Now I'll come back to solving, going back to this tutorial, the lecture itself. Because I'll wind up the discussion with common emitter. So far we have analyzed what we call as a resistive load. So we have a common emitter amplifier, and then I connect a resistor to it and try to get amplification out of it. In practice, in most of the cases, when we build transistors or amplifiers inside an IC, we have what we call as an active load. See, For example, whenever I represent a BJT, I represent a load like this, a current source load ICQ. But how do I implement this current source in a circuit? Okay, there are circuits which can implement that current source itself. See, there is no real current source, right? Somewhere we have to build a circuit for this also, a current source as well. Okay, similarly, voltage source. We are saying voltage source, but there is no real voltage source. So we have to build that voltage source also. So whenever I represent a voltage source like this, if there are circuits which can generate this voltage sources as well. Okay, so those we won't talk about those circuits, but a slight approximated versions is what we will discuss right now. I'll then finish the discussion of common emitter configuration with that. That is why I wanted this one extra lecture, so that I'll discuss that off. So now we will try to realize a current source using a BJT. What is the property of a current source? Even though the voltage across the current source changes, the current should remain the same. That's the definition of a current source. Now we know this is the IC versus VCE characteristics of a BJT. Now if you notice a BJT in this region, if you noticed it in this region, okay, even though the VCE is changing here significantly, the collector current doesn't change at all. I can then say that the BJT is going to behave like a current source in this region. Okay, now understand this, VB is fixed here. Because your collector current, look at this, the collector current has only a dependence on VB. So what will I do? I'll take a BJT, for example, in NPN transistor, and fix the VB quiescent. I'll always force it to a fixed voltage. I won't let the voltage change. Then the current flowing through this will always remain constant independent of the voltage across it, as long as VC is greater than 0.2. As long as your VC is in a certain range, it's going to behave like a current source. So BJT can be used as a current source. If you bias it appropriately, a BJT can be used as a current source also. Now, this is what is the model for a BJT. So this is collector terminal, this is emitter terminal. Between collector and emitter, the BJT is going to behave like a current source. Now the quiescent collector current is given by alpha Is into e power VB by VT. So this is fixed. Because VB is fixed, ICQ is also fixed. Therefore it behaves like a ideal current source. Okay, but in reality, now, but the important thing to note here is that usually a current source is a two-terminal device. You will have both terminals accessible. But if I use a NPN BJT, one terminal will normally be at ground because it's the sinking current. This is called as a sinking current. Sinking current is current always goes into the ground. It's called as a sinking current source. Okay, it's a sinking. The word is not clear, so probably it is a sinking current source. Okay, so one node is at ground, the other node is free. As long as the voltage across this is greater than VCE SAT, which happens to be 0.2 volts, you're fine. You will be in this range. The device is going to behave in this range, it's going to behave like a current source. So therefore, I can use a BJT itself as a current source. If I fix its VBE voltage, then between collector and emitter, it will behave like a current source. Similarly, I can use a PNP transistor. I'll take a PNP transistor. Usually PNP, one end is connected to supply voltage. The base, I am going to connect it to VDD minus mod VBEQ. So that the voltage across the BJT, the VBE of this is mod VBEQ. So I'll forward bias this junction. Then between collector and emitter, so if this is collector, this is emitter, this is base for a PNP transistor. It is going to behave like a current source. As long as the mod of, I didn't talk about PNP transistor, but for a PNP transistor, if you just take mod of ICQ and mod of VCE and mod of VBEQ, it will have the same graph. IC versus VCE graph will look similar. So this is mod of VBE. Okay, this is mod of VBE. So a PNP transistor can be used as, this current source is called as a sourcing current source. It's called as a sourcing current source. So now what will I do? I can, for example, if I give you a circuit like this, this is V0, this is Vi. I can then replace this upper current source with a PNP transistor. Fix this at some VBE voltage, VB, some bias voltage, which is VDD minus mod VBEQ. Then these two circuits are equivalent. Both the circuits are equivalent. I'll choose the dimensions of this BJT or the VBE of the BJT in such that the value of the current flowing through this is same as this current. Okay, I can do that, right? I can find out the quiescent current or VBE necessary to get the quiescent current.
So,
Yeah.
in that about transistor, shouldn't the emitter be shorted with the base
Which one?
in that equivalent circuit?
No, no, no. Emitter and base cannot be shorted. So that it let me draw it properly. So you need a current source, right? If you need a current source, what should you do? You should take a PNP transistor. Base is connected to. Yeah, I'll tell you that. See, what was I telling you? If you took a, see, what do I need? This is NPN transistor, and I need a current source like this. One end of the current source is connected to supply, let's call it VCC. Other end is connected to the transistor. Okay, I just told you guys that a PNP transistor, if its VBE is fixed, let me show it even properly. If let's say this node is at VDD or VCC, let me call this VCC. This node is at VCC. This node voltage, I will keep it in such a way so that it is VCC minus mod VBEQ. Then the collector current in this NPN transistor, ICQ is given by alpha IS e power mod of VBEQ by VT. Now what will I do? I will find out what should be the value of mod VBEQ, which will be VT ln of ICQ by alpha IS. Okay, just find this, sign this equation, you will get it. I know ICQ, what current I need. VT is fixed. I also know the saturation current of the transistor. Usually that will be given to you. Then I will know what is the VB necessary to get that current. That I will ensure that the VB of this MOSFET is same as this VBEQ. What I am saying is, if I ensure that, then between collector and emitter, between these two terminals, the BJT will behave like a current source. Now look at this current source. On one side it is VCC, which is VCC. Other side it is free. But there is a condition. The condition is that the voltage across the current source or the voltage across the BJT should be greater than VCE SAT, which is 0.2 volts. It should be greater than this. Only then it will behave like a current source. And how am I saying that? I am just looking at the IV characteristics. So this is 0.2 VCE SAT. If your voltage is in this range, then the BJT is going to behave like a current source. Right? What is the definition of a current source? Even though the voltage is changing, current is constant. That's the definition of a current source. Okay? So what I was saying is that I am starting from a circuit like this, which is an NPN transistor with a current source load. This is called as a current source load. Now I need to replace this current source with a BJT implementation. I just told you, and look at this current source. On one end of the current source, it is connected to VCC. Other end, it is connected to a BJT, which is free to move. So what will I do? One end, I'll replace it with a PNP transistor like this. So this node will be VCC minus mod VBEQ. And I'll find out VBEQ using this equation. The equation we have is mod VBEQ equals VT ln ICQ upon IS, alpha IS. From this, I'll find the value of VBEQ and apply that voltage across this junction. Then between this terminal and this terminal, this PNP transistor will behave like a current source of value given by I. Okay, or this will be I. Instead of ICQ, I can call it I. Okay, I'll come to that. I'll come to that. Yeah. So this is I. Now I'll then replicate the same lower part as it is and keep it like this. So this is Vi, this is V0. Okay, now this question is, can I use NPN transistor? Now look at NPN transistor. I told you guys NPN, the problem with NPN is that usually yes, you can use, but then the problem with NPN is one terminal is at ground. You cannot get that free accessibility. This emitter is at ground, right? So you will get that emitter terminal at ground. So I can't use, I need a current source like this. One terminal should be at supply voltage, other terminal should be free. That's called as a sourcing current. If I have a sinking current, one terminal will be at ground, other terminal will be free to move. That's called as a sinking current. So to realize a sinking current, I need an NPN transistor. To realize a sourcing current, I need a PNP transistor.
So,
Yeah.
is there any advantage of using a sinking current source?
No, see, for example, it's not about advantage, it's about implementation, right? So, for example, let me show you a circuit like this. This is a common emitter amplifier. Let's say I'm biasing this using a current source. Okay. Now, what kind of a current source is this?
A sourcing current.
Yeah, it's a sourcing current source. So then, if I want to implement this using a transistor, the only possible implementation is a PNP. I can't use NPN for it because it's a NPN will give me a sinking current source.
So what I meant to ask was,
Huh.
do we use sinking current source at any devices?
Generally, yeah, we will use. I'll show you an example. Now, let's say we have a PNP common emitter amplifier. In a PNP common emitter amplifier, it will look like this. You'll apply a Vi, and this is your output V0, and a current source ICQ here. This is a PNP common emitter amplifier, right? This is also, see, this is emitter, base, collector, right? This is a PNP transistor. So look at the input is at base, output is at collector. So the third terminal is common. So for this, it is emitter. Okay. Common terminals will either be at the ground or they will be at the supply. As far as AC is concerned, they both are grounds, AC grounds. So you see this, right? Here I am using a sinking current. That's an example. You are asking, will we use sinking current at all? The
Yes.
answer is yes, yes. This is an example of a sinking current. So now we'll have a current source like this. This I will fix it to a voltage source of value, some VB quiescent. Then this is Vi and this is V0. That's it. So this is what I call as a common emitter configuration with active load. So this is called, instead of resistor, I'm using BJT. BJT is an active device, so it's called as an active load.
So
Yeah.
in a sourcing current source, the other terminal is free, right? So it can be connected to ground also.
Yes, it can be connected, but what is the point? See, let's say you have a current source. One terminal is VCC, other terminal is ground. Then what is the point of the current source? It has to go somewhere in the circuit, no?
Might Yes, sir, makes sense. But in this case, we can use a PNP transistor also, right? Like it's not compulsory to use only an NPN transistor for the second example.
No. See. The thing, the problem is that if you need a sourcing current, you cannot use an NPN transistor.
Yes, sir.
Because why? One terminal is always connected to VCC. Okay, sorry, you want an sourcing current? Yeah, one terminal in an NPN transistor, one terminal is always connected to ground. Only this terminal is free.
Yes, sir.
So sinking current, NPN, sourcing current, you will be using, see, what you are asking, okay, I will connect this terminal to ground. So now, but see, this is no longer a useful current source, right? You have already used it between VCC and ground. So what is the point of the current source? There is no use for it. There is no practical use for it.
Sir, my doubt is that uh, for this example, we can use both a sinking current source or a sourcing current source and connect the pre terminal to a ground. Both of them are the same thing, right? Or are they different?
Okay, yeah. In this example, yes. You can realize this structure using either a BJT or a MOS. I mean, either an NPN or a
Yes,
PNP.
sir. That was my doubt. Thank you.
But yeah, okay. But this is like not a realistic scenario, right? This is the more realistic. What I've shown you two realistic scenarios. Yeah.
Yes, sir.
Okay. So this is a PNP with a current source. So this is called as a current source load, and that is realized using a PNP transistor or NPN or PNP transistors in a active regions. Now, in reality, what happens is ideally, what is the definition of a current source? Even if the voltage changes, the current should remain constant. But we know that most practical current sources will have a slight increase in the current. And we said this, the 1 by slope of that will be the resistance of the current source. I already discussed this, I think, in the previous lectures. So in reality, if you take a BJT, if I fix my VBE voltage to some VBEQ and you vary your collector to emitter voltage, then the current will also increase slightly. And we know the slope of that is 1 by R naught, right? We know how to find the slope. Now, therefore, the actual model of a NPN transistor used as a current source will look like this. There is a constant current source ICQ. In parallel with it, you'll have a voltage of a resistance of value R naught. R naught is early voltage upon ICQ. This is your R naught. So this is a practical current source. A practical current source will have a finite resistance in parallel with it. Okay. So BJT can be modeled as a current source for a given VBE. It will be a current source and a resistance in parallel. This is clear, right? So similarly, NPN transistor, that will also have a finite R naught, and that can also be modeled as a parallel resistance of value ROP. See, generally these are the terms. For NPN transistors, we call it as RON, and PNP it will be ROP. So generally we will give you early voltages for NPN, early voltage for PNP. The way in which we give you questions is that we will give you a table, we will give you NPN, PNP, we will give you the beta values for you to use, then we will also give you the early voltage values for NPN and PNP, we will give you the values, then you should read from the table and use it in the calculations. So typically we will do that. Okay, sometimes we might even give you reverse saturation current for NPN and PNP. So the table,
Sir,
yeah.
so can you discuss like from BCC minus BEQ that circuit to right circuit? How do you derive it?
No, see, let me show. So let's say we have a PNP transistor. Now, how do you plot the IC versus VCE of a PNP transistor? So this is your VBE for a PNP, right? So see, this node voltage, if I want to bias this PNP with a voltage of VBE, so let me write it, this voltage is mod VBEQ. That is your base emitter voltage. This is PNP transistor. So then this node voltage will be VCC minus mod VBEQ. That will be this node voltage here. Okay. Now what I'm trying to tell you is that if you plot the IC versus VCE characteristics of a PNP transistor, it's exactly the same as an NPN transistor. The graph will look the same like this. Okay. Everything will look the same. The only difference is you'll have to take mod of all the quantities, because all the quantities will be negative in NPN. You'll have to just take mod of VBE. That's it. So the same rules apply. If you take the voltage across this VCE and take mod of this, it should be greater than, in fact, VEC should be greater than 0.2, VEC sat. So this is VEC sat. The emitter to collector voltage should be greater than 0.2. So this voltage, as long as this voltage across this is greater than 0.2, this will behave like a current source. So what I'm trying to tell is the voltage, even though the voltage is VCE is changing, the current is always constant. It's constant, it's not changing. It is constant only in active region, right? What is the active region condition? Base emitter junction should be forward, emitter base junction should be forward, this junction should be forward biased, this junction should be reverse biased. That's the active region condition. If you satisfy this condition, then you will be able to get a sourcing current. Now sourcing is PNP, because see, usually sourcing you look at this way. You are sourcing this, you are providing this current. You are providing this current into a circuit. See, for example, I've shown a BJT here. I can also have some circuit here. So this is called as a sourcing current. Okay, the current is being sourced into the circuit. Sinking current, from where did we get DC greater than 0.2? Okay, V is EC. Okay. Now, do you understand that for a NP and BJT, how did I write VC greater than 0.2? I just took that as a value. I didn't say 0.2 necessarily. It's VC greater than VC sat. Is this clear to you, at least NPN, the graph of NPN, the BJT's characteristics? Okay. See, let me answer that. See, what is VCE? In an actual BJT, what is VCE? VCE can be written as VCB, the collector base junction. So this is an NPN transistor. NPN transistor minus VB. Am I right here? Is this right? Minus VEB, right? This should be minus VEB. Am I right here? So you need to write it as, see, this is the collector voltage, this is the emitter voltage. So this is VCB plus, okay, so this is VBE. So the VCE will be equal to VCB plus VBE. This can also be written as VBE minus VBC. Okay? Okay, so now if you see this result, yeah, I think I've written it right here. Am I right in writing this result this way? Base is the common terminal. Base is the common terminal, so we can write VCB minus VEB. Okay, so then this can be written as VCB plus VBE. Yeah, fine. VCB will be negative. VCB in that case should be negative, so which will be a reverse bias diode. Yeah, VCB is a reverse bias voltage. Okay, and if VBE is forward biased, let's assume this diode is forward biased, that is VBC is forward biased. In that case, VCB will be negative. Okay, so let's assume VCB is forward biased. Usually what happens is we assume the result 0.2 comes from devices. When I was teaching devices, the way in which we derive it is, if you see how does your junction voltages scale? This is NPN. I told you this is N plus plus P plus N. Right? This is the way the junctions are. So which junction will have a higher built-in potential? Which junction do you think will have a higher built-in potential? Built-in potential depends on what? VT ln VT ln NA by NI square, right? So the higher, whichever region has higher depletion, the doping concentration, that will have a higher built-in potential. So this region obviously will have higher built-in potential, this one, compared to this. So this value VBE plus VCB can also be written as VBE minus VBC. Okay. Now I'll assume that for if VBC is forward biased, then this will be close to 0.5 volts. this will be close to 0.7 volts. Okay, so the difference comes to around 0.2 volts. That's just a rule of thumb. Okay, it will be smaller than that also. It can be even smaller than that. So now if VPC becomes negative, then this quantity will become negative and your device will be properly in active region. Base collector is reverse biased. If it is forward biased, if it gets forward biased, then it should be greater than 0.5. Right? See, why am I taking 0.7 points? I'm just telling you that base emitter will have a higher built-in or slightly higher cut-in voltage as well. And this guy base collector will have a slightly lower cut-in voltage. So from that I can say 0.7 minus 0.5 approximately is 0.2. Okay, a 0.2 is just like a number. We usually we will give you the VCE SAT. VCE SAT will give you as 0.2 or even 0.1. We will give you that. Okay, that's how this VCE SAT comes from. So now if I assume base collector is in forward region, then VCE becomes 0.2. When it is in 0.2, VCE SAT is 0.2, then the PNP transistor is in, it's on the brink of saturation. It's just on the brink, right? This device is also about to conduct and this is also conducting. Now, if this goes deeper into conduction, which means if VBC becomes greater than 0.5, VC will become less than 0.2. So then the device is going into linear or ohmic region. Okay, so that's how this 0.2 comes from, roughly. Okay, I'm giving a rough expression. Rather, I should have used VCE SAT instead of 0.2. I should have used VCE SAT. But what did they teach you in devices? Did they teach you 0.2 or what did they teach you in devices? VCE SAT, is it? Okay, yeah, fine, that's okay. I just gave it as 0.2, but as I said, it is VCE plus. You can, sorry, VCE SAT. You can treat it as VCE SAT. Okay. See, what was the doubt? You guys were asking me how you want me to show how is a PNP transistor used as a current source. Yeah, and yes, it is. Is that the doubt? What did you ask?
Sir, I asked the ROP part.
Oh, ROP part is same as the small signal R0. There will be a finite slope here. Extend the slope. See, if you understood it for NPN, the same thing happened for PNP also. Same base width modulation. So the current will increase and all of that. So the slope
Oh,
of this is 1 by R0. That's it. Yeah.
oh, okay, sir. Got it. Thank you.
Yeah. So, yeah. So we have seen two current sources. Okay. One is what we call as a sourcing current source. Let's assume this is plus VCC. You have a circuit like this connected to ground. This current is being sourced to the circuit. There can also be another circuit which can be connected to, on one side it will be connected to VCC. Other node you can connect, this current is actually sinking the current. This is a sinking current source. It's like a current sink. Okay, it's taking current and injecting into the ground. Now what I'm saying is the sourcing current can be replaced. You can generate it using a PNP transistor by choosing an appropriate voltage, fixed voltage. For it to behave like a current source, this voltage cannot change. That has to be fixed. Only then it will behave like a current source. Then I said between these two terminals, this BJT will behave like a current source, provided you ensure this voltage is always greater than 0.2 volts. As this node voltage increases, this voltage will reduce. But if you ensure that as long as this is greater than 0.2, I'm just using 0.2, rather let me put it as VCE SAT. We will give you this value. If it is greater than this, it is in active region, which means it will behave like a current source. The same way, a sinking current source can be replaced and realized using a NPN transistor. I'll call it as VB quiescent. This is ICQ. Okay, as long as this voltage is greater than VCE SAT for an NMOS, it's all fine. In addition to that, the practical model, we said, okay, a PNP transistor is going to behave like a current source, but in reality, a PNP current source, a PNP transistor has a finite R0 when it is conducting current. So that we said it's not just a modeling a current source alone, it's also modeling a resistance in parallel with it. And I'm calling it as ROP. How do you get ROP? If you know the bias current value, and usually we'll give you the early voltage as well. I'm calling it BAP by ICQ. We will give you this, from that you can calculate. And I told you how will we give it. Usually in the question paper we will give you like this. So we'll have tables for NPN, PNP, and it will be given like this: beta, reverse saturation current, early voltage, and then we'll give it for NPN and PNP. We may not give you in the question. If it's not given in the question, refer to the table and write it down. That's it. Okay. So VA will be given for this will be VAN and VAP. So from this you use this, and collector current quiescent will be usually be given in the question itself. Okay. That's it. So now I'll just show you guys two amplifiers, common emitter amplifier. This is with a NPN common emitter amplifier. This can be realized by replacing the current source with a PNP device like this. So this is at some DC voltage VCC minus mod VBEQ. I don't need to specifically write this value. I can simply say some VBP, some bias voltage here. Okay, where the bias voltage value should be VCC minus mod VBEQ. You will choose that value to be this. Now, if I ask you to find the voltage gain of this circuit, what will it be? What is the small signal resistance offered by this device, PMOS? What is the small signal resistance offered, incremental resistance offered by this? We just discussed, no? For a PMOS, current source is sourcing current, R naught, right? R naught P. Let me call it as R naught P. That's it. Take your NPN transistor, replace this with, for small signal, this node is at AC ground, and this is your output voltage, this will be R naught P. And now we will quickly draw the small signal model. So you will have GMV pi. This is your R naught N for NMOS, NPN, and R naught P is your load. That's it. So this is your output voltage. I have drawn the small signal here. Okay. So now what is the intrinsic gain in this case? I have replaced this NPN transistor by its small signal model GMV pi RON, and ROP I have retained this as it is because this node is at AC ground. ROP will come in parallel with RON. ROP is the resistance of your NMOS device, NPN transistor.
Sir,
Yes.
so BJT is a current device in parallel with ROP, right?
No, the lower BJT we are applying the signal.
No, upper BJT, sir.
Upper BJT is PMOS. It is it's actually a current source and a resistance ROP in parallel. But when you draw the small signal AC model, what will you do? You will open circuit current source. You will remove the current source.
Okay, sir.
Short circuit the DC source and then replace 25 ROP. Okay? Yeah.
Sir, shouldn't there be another current source to of ICQ?
Shouldn't there be?
Another current source of ICQ.
Yeah, that's what. No, this is small signal model. What I have drawn here.
Okay, so you've shorted it.
Open
Oh no,
circuit.
you opened it.
Yeah.
Okay, fine.
You should make current as 0. Yeah. Okay. So this is the small signal or incremental model. And so what will be the gain? What will be the gain you will get? GM into minus of GM into ROP parallel RON. So now express your gain in terms of VAN and VAP. Can you express your gain in terms of VAN and VAP? Assume GM as ICQ upon VT, ROP as VAP upon ICQ, and RON as VAN upon ICQ. Express your gain now in terms of, will it depend upon ICQ? I just want you to find out. Will it depend upon ICQ? So minus GM into, why ROP and RON parallel? Okay, fine. Let me just, okay, I'll just, rest of you can keep doing that. I'll just explain this. See, you can replace your PNP transistor by a sinking current source of value ICQ and a small signal resistance of value ROP. This is connected to VCC. Okay, this is your output node. Now, what are we trying to find out? We are trying to find the small signal AC gain for the circuit. In a small signal AC gain, this ICQ is a DC current source. So I should open circuit DC currents. I should make current as 0, which means current is open. I should short circuit supplies all the DC voltage. So this will be short circuited. Okay. Now if you draw the small signal model, for this BJT, you have a resistance RON between collector and emitter. Emitter is ground, RON. So now you see, this end, see, two resistors are said to be in parallel if both the nodes, if they share both the nodes. Now look at this ROP. This collector resistance is collector node is same for both, and also the other end is ground for both. AC ground for both. So therefore they both are in parallel. Okay, yeah. So now we'll substitute it and find out. So GM is ICQ upon VT. I will write it this way. What is ROP parallel RON? I can write it this way. Let me call it as R equivalent. So 1 by R equivalent will be 1 by ROP plus 1 by RON, right? They form a harmonic mean. So therefore 1 by R equivalent will be ICQ upon VAP plus ICQ upon VAN. So therefore this will be ICQ upon 1 by VAP plus 1 by VAN. This is your 1 by R equivalent, which is 1 by ROP in parallel with RON. Okay. Now your overall gain will be minus of GM into ROP parallel RON. So the whole inverse of this. So minus of GM is ICQ upon VT, and the whole inverse of this. So you will get an expression like this: 1 by VAP plus 1 by VAN, the whole inverse into 1 by ICQ. You cancel out, you will be left with this. You must have gotten, yeah, most of you I think got it right. So VAP VAN by VAP plus VAN into 1 by VT. So now again, if you see, this gain also is independent of the bias current. So I think this was one of the questions we asked twice almost in your previous years. So we had given a current load BJT circuit and expected you to find the voltage gain, and we asked, let's say we double the current. Now what will happen to your voltage gain? Okay. No, R pi is not infinity in the case. R pi is still present, but it doesn't figure in the gain. I have applied, this is an unload, you can treat it like an unloaded gain, VI directly here. So VI equals V pi. Otherwise, I'll have to calculate that also. There's no RS, yes, yeah. Okay, so this is something we gave. Then we asked you, okay, if your bias current changes, will the gain change? But the answer is no, it doesn't. It's independent of the gain. Okay, so I'll just finally solve your tutorial final problem. So you can, and then you can ask me doubts. We'll finish this. That's it. We are done with this problem now. So I've discussed current source loads in one lecture. Yes, no, I mean, gain depends on bias current only in some specific example. We took an example, right? Yeah, I'll scroll it up. See, we took a specific example where we said, let's assume we have a circuit like this. In this circuit, so this is VI. In this circuit, we said the gain, if you assume R0 is infinity. I have given an example when R0 is infinity. In that specific example, R0, the gain happens to be minus of GM into RL. In this case, your gain depends upon ICQ. It does depend, but intrinsic gain doesn't depend upon ICQ. Intrinsic gains, generally, intrinsic gains doesn't depend, and also gain with active loads. If I use a PNP active load, gains don't depend upon bias current. But in general, it can depend upon. Intrinsic gain, I'm being very specific, intrinsic gain doesn't depend upon bias currents. Okay guys, I'll just discuss this one last problem. I think you're done with this. So, if you're
Sir,
done.
can you scroll up a little bit? Yes.
Okay, I'll just solve the final problem in tutorial and we'll be done with tutorial question. Okay. Now look at this. This is the question given to you. You are supposed to find the voltage gain of this amplifier stage by stage. You are supposed to find two stages. So this is VO1, and so you are supposed to find VO1 by VI and V0 by VI. So whenever you are given multiple stages like this, right, go stage by stage. Okay, you can draw the small signal model and analyze it stage by stage. Let's look at the first stage. First stage, there is R pi, which is beta is given to be finite, but VI is infinity. So which means R naught is infinity. For all transistors, R naught is infinity. So I don't have to worry about R naught, I have to worry only about R pi. Nothing else is given in the question. So now if you see, first stage, Vi equals V pi, I'll try to analyze the circuit intuitively without even using KCLs. Then I'll give you guys the small signal model. As soon as you apply a voltage V pi, which is nothing but Vi, now picturize in this, look at this, this is one more important thing. Most of the times in the circuits we give you in exams, we may not even show you the biasing circuitry. And we'll ask you to assume the devices are biased in saturation or active region. We'll ask you to assume that. Okay, so that's an example here. So now you are supposed to perform small signal. You are applying a small signal voltage Vi. In response to that, BJT will generate a current flowing from collector to emitter, current of value GM Vi. Right? Vi is VBE, VBE is Vi. So you get GM Vi current here. Now this current GM Vi is flowing in this direction, or I can assume it is flowing, a current of minus GM Vi is flowing in this direction. Now quickly tell me, what is the input resistance seen here of the next stage? That current is going to flow somewhere, right? It's going to flow into input resistance. What is the input resistance? Is everyone okay with that? What is the input resistance? This is a BJT. You are looking into the base of other transistor. Is that okay? You see, this is a NPN transistor, right? Yeah, you're looking into the base, so the resistance is R pi. Yeah. So now this current has to flow into R pi. If this current flows into R pi of Q1, yes, R pi of Q1. But they are all identical transistors. I've given in the question that they are all identical. Because they are identical, you will have a voltage gain of GM into R pi into Vi. So what is the value of GM into R pi? Beta, right? This is beta. So it will be minus of beta into Vi. So the voltage gain VO1 by VOY is 100. Beta is given to be 100. Now let's find the voltage gain of the second stage. Now if I'm applying a voltage of VO1 here, the current that is going to flow through this is GM VO1, because VO1 is VB of the second stage. GM VO1. That GM VO1 current will now flow into, again the same thing, Q3. If I'm looking into the base, emitter is grounded, the input resistance offered here is R pi. So you can visualize that there is a resistance R pi between base and emitter. Right? In the small signal model, you can visualize that. So this current GM V01 will flow through this. So again, the second stage gain will be minus of GM R pi into V01. That is also beta. So what is the overall gain? Overall gain from V0 by Vi, what will be that? Beta square, yeah, 100 square. That's it. Okay, it's a very interesting circuit if you think about it. I'll mention one interesting thing called, they must have taught this in your devices. It's called as a Darlington configuration. Okay, what they used to do is that, let's say you take a single BJT. If I use a single BJT, let's say IB with the base current. What is the collector current in terms of base current? What is the beta value you get? I mean, so what will be the collector current in terms of beta base current? It will be beta times the base current. Right? It will be beta times the base current. Sometimes what happens is in ICs, you get a beta less than 100. In fact, you will get a beta of 20, I said. What if you want a higher beta? If you want a higher beta, we do what we call a Darlington configuration because it's just a scientist who invented it. What we do something like this. We take this base and short circuit these two collectors. Now this transistor will behave like a composite transistor with three terminals. This is the base of the overall transistor, the collector of the overall transistor, emitter of the overall transistor. Okay, this is one way of generating a device with a higher current. Or there is other way of doing it as well. You will take one transistor this way and okay, I think that will be a little complicated. You can just look at this itself. Okay, so now if this is IB, let's say IB is flowing in this direction. What will be the emitter current here? Can I say it is beta plus 1 times IB? That will be the base current of the next guy. If this is beta plus 1, what will be the current flowing through this? Beta into beta plus 1. Okay, beta into beta. So that I can approximate it as beta square. This is beta square. Okay, so now this current here will be beta times IB. This current here will be beta square times IB. Okay, it is in fact beta into beta plus 1. So the total current here will approximately be beta square plus beta into IB, which is again approximately equal to beta square. Beta square will be much greater than beta, right? Beta square will be much greater. So I'll ignore smaller beta and I assume it as beta square IB. Now I have a composite device with an effective current gain of beta square. Okay, the effective current gain of the circuit is beta square. This is called as a Darlington configuration. If you want higher current gains, we use a configuration like this. Okay, so now let's come back to this circuit. Let me ask you a simpler question here also. Let's measure the current gain from, let's assume you are injecting instead of voltage, you are injecting a current of value IB here. What will be the current at this output? Can I say it is beta times IB? It's a BJT, right? Beta times IB. So what will be the current here? If this is beta times IB, this will be beta square times IB. Okay, so that's it. So now if you see the current flowing here, it will be beta square. Here it is beta times IB, it is IB here. And you look at it, at each node, the input resistance is R pi, input resistance is R pi, input resistance is R pi. Input resistance remains the same, but the current increases exponentially. So therefore the voltage will also, if this is Vi, this will be beta times Vi, this will be beta square times Vi. The voltage gain increases because there is a current gain itself. Current is getting higher and higher. Impedance is changing, remaining the same. This is okay. What I'm trying to say is that look at the currents. The currents has become IB, beta times IB, beta square IB. It is just increasing. And that's how we are getting the voltage gain.
Could you upload these slides, please?
The slides I will not, but video I'll upload because it seems the other instructor asked me, IC asked me not to because, yeah, so he had given some reasons. So we decided not to upload slides, but I'll upload the video. Okay, so we are done, guys. So you can go through this. See, but in the slides also, I don't explain this current gain and all that. You have to go through the video to understand all this. It's better that way. Yeah. Okay, guys, I think we are done with today's class. Okay, so we're done. You can leave.
Sir,
Yes.
sir, if VO1 and VI amplification is asked, should we write minus 100 or 100?
Minus 100. A single
Okay,
common emitter. See, one more thing. A common emitter amplifier will always give you a negative gain. Okay. Yes. If you cascade n amplifiers, exactly. That is right.
Okay, thank you, sir.
Yeah. You're right. If you cascade n amplifiers, we are going to get n beta power n, I think, right? There are two stages here. Two stages give you beta square. Three stages will give you beta cube and so on. So it will be beta power n. Yes. It's not beta power n minus 1. It will be beta power n.
So technically we can go to infinite amplification with this.
No, see, infinite amplification is possible even with not only this, right? You can directly use a load resistance as well, finite load resistance as well.
Yes, yes,
Okay, you can use, I mean, you can get, if you keep cascading amplifiers, we can get as much gain as we want, but usually we avoid doing that. You will see later towards the end of the course why we avoid doing that. We don't do that. We try to do it just necessary. We won't, when you cascade, encounter problems of stability. That we'll tell you in the middle of the course, at least in the second half of the course. If
okay, thank you.
Q2, yeah, if Q2 would have been open, then there would have been beta cube, right? If Q2 is open, okay, I mean, if Q2 is open, then if you measure the current through this, no, even if your Q2 is closed, if you measure the current, yes, it is beta cube times IT. The current through this. It's beta cube, yes. The gain part, voltage gain, I explained it, right? Voltage gain is beta square. So, see, how do you find voltage gain? You applied a voltage VI, a current GMVI flows here. The input resistance here is R pi. Okay, you can see it from the small signal model. This is the small signal model. The first BJT goes to the second BJT, then goes to the third BJT, where it is shorted like this. So look at the first BJT, VI equals V pi. Second, now this node is VO1. This is V pi 1 is actually VO1. That's what is given in the circuit. Okay. So then what do you do? Apply KCL at this node. So the first stage gain will be minus of GM V pi into R pi of the second stage. So that will be minus beta times V pi. V pi is VI. So the first stage gain is minus beta. Till this point, the voltage gain is minus beta. Similarly, perform the second stage also. This node voltage will be minus of beta for the second stage. So overall two-stage gain is beta square. Minus beta into minus beta. So minus beta into minus beta. Total or overall gain will be beta square. Is that okay? Or, I mean, I didn't understand. Yeah, okay. Yeah, okay guys. Thank you. So I'll stop recording now.